Now let's examine probability when permutations and combinations are involved. Let's suppose that we draw 5 cards at random from a standard card deck. First, let's figure out the probability of getting 5 spades. So our event now is 5 spades. Our sample space is the set of all possible 5-card hands. How many 5-card hands are possible? Well, how many ways are there to draw 5 cards? When we draw them from the deck and put them in our hand, the order does not matter. Whatever order we receive them, we still consider it the same hand. So that tells us we use a combination. There are 52 cards in all. We are going to choose 5 to be in our hand. Now, how many are in our event? This is going to be the set of all cards that have 5 spades. How many ways are there to get 5 spades? Well, there are 13 spades to choose from. We will choose 5 to put in our hand. So the probability that this event occurs, everything is equally likely. Every hand is just as likely as another. So we're going to take the number of outcomes in our event and divide by the total possible number of outcomes in our sample space. So our numerator is combination 13, 5. Our denominator is combination 52, 5. So this gives me 1,287 divided by 2, 598,960. And so we end up with a probability of approximately 0.000495. Now let's determine the probability of getting 2 kings, 2 queens, and a jack. Our sample space is the same as before. And so the number in the sample space then will be combination 52, 5. In other words, our sample space will be all the possible 5-card hands. How many are in our event? Okay, how many ways are there to choose 2 kings? We're going to have 2 kings. We're going to multiply that by the number of ways to get 2 queens. And we're going to multiply that by the number of ways to get 1 jack. There are 4 kings altogether. We're choosing 2 to be in our hand, so we get combination 4, 2. For the queens, there's 4 queens altogether. We're choosing 2 to be in our hand, so we get combination 4, 2. How many ways are there to choose 1 jack? Well, there's 4 jacks in the card deck, so there are 4 ways to choose 1 jack. So our probability then, once again, we take the number of items in our event and divide by the total number of possibilities in the sample space. So we get combination 4, 2, combination 4, 2 times 4 divided by combination 52, 5. So we end up with 5.5407 times 10 to the negative 5, 0.0000055, remembering to move our decimal point by 5 slots since we have 10 to the negative 5th. So not a very likely outcome. Let's look at another example. Let's suppose that Joe and Susan Thomas work in a department with 12 other people. 4 employees will be chosen at random to attend an important conference in the Bahamas. What is the probability that both Joe and Susan will be chosen? I should have written on here, let's assume they are chosen randomly. Maybe we put their names in a hat or something like that. In that case, every outcome is equally likely. My sample space will be all the ways that 4 people can be chosen. Okay, so our probability then will be the number in our event divided by the number in our sample space. First, let's look at the number of ways that 4 people can be chosen. That'll be our sample space. How many people work in the department altogether? Well, there's Joe and Susan, and then there are 12 other people. So that means there's 14 employees altogether. We're going to choose 4 of those 14 to go to the conference. Okay. So now, to figure out the numerator, how many ways are there to choose Joe and Susan? Well, there's only one way. Either those 2 are chosen or they're not. There's only one way that Joe and Susan can be chosen. So that's 2 people chosen. Now we need to choose 2 more people. How many people are left? 12. How many are we choosing to go on the conference with Joe and Susan? 2. So we get combination 12, 2. We multiply it by 1 because there's one way to choose Joe and Susan. And so this is 66 divided by 1001, which is approximately 0.0659. So they shouldn't count on this as their vacation together because it's not a very likely thing to happen. Let's move on. Let's suppose that you had written 6 thank you cards and addressed 6 envelopes. And while you're away, you have a young child who decided to be helpful, put the cards into the envelopes at random, stamped, and mailed them for you. What is the probability that all the cards were put into the correct envelopes? Okay, and then we want to figure out the probability that only 2 were sent to the wrong people. So, first of all, let's figure out our sample space. Our sample space will be the number of ways in which the 6 cards can be sent out. So, there will be 6 possibilities for the first address. There will be 5 possibilities for the second address, 4 for the third, and so on. Anytime you are being asked how many ways are there to arrange 6 things among 6 slots, the answer to that would be 6 factorial. This is how many possible ways there are for those 6 cards to be distributed among the 6 addresses. How many correct ways are there? There is only one way for this to happen. If you do not get it exactly right, then someone, at least one, gets the wrong card. So there's only one correct answer for this. So there's only one way to get them all into the envelopes correctly. So our probability that this happens, guess here we're on part A, will be 1 over 6 factorial. 1 over 720, which is approximately 0.00139. So you should probably be prepared to apologize for someone for sending them the wrong card. Now let's look at the probability that only 2 were sent to the wrong people. So that means that 4 are correct and 2 are wrong. How many ways are there to choose 4 to be done correctly? There are 6 cards. If we choose 4 to be correct, that means we've got combination 6, 4. Now, how many ways are there to choose the 2 that will be wrong? Well, the 4 have already been chosen, so that means there are only 2 left to choose from. How many ways are there to choose those 2 to be incorrect? Well, there's just one way. Since there's only 2, there's only one way to get those 2 wrong. There's only 2 that can be chosen, and there's only one incorrect way to rearrange them. So our probability then will be combination 6, 4 multiplied by 1. Divide that by 6 factorial, the number in our sample space. So we end up with 15 over 6 factorial, which is 15 over 720, approximately 0.02083. Let's move on. Suppose that we have a shipment of 100 radios in which 3 are defective. Quality control engineer selects a random sample of 5 radios. What's the probability that at least one radio in the sample is defective? Okay, so our sample space would be all the possible 5 radio samples. All the ways that 5 radios can be chosen. Now, how many of these are there? Well, how many are we choosing from? 100. We're choosing 5 of them. So we get combination 100, 5. It'll be the same sample no matter what order we choose them in. So we want to use a combination and not a permutation. Now, since we have at least one defective radio, that's very important. That means we can have 1, 2, or 3 defective radios in our sample. We have 5 in our sample. Why can't we have 4 or 5 defective radios in that sample? That's because there are only 3 defective in the whole entire batch, and so it's not possible to get more than 3 defective. So if at least 1 is defective, that means we're going to have 1, 2, or 3 defective radios. Okay, so we have 3 that are defective, and so how many of the 100 are good? 100 minus 3, so 97. That tells us how many good radios we have to choose from. So let's suppose that our possibilities are we could have 1 defective, and we could have 4 good in our sample. Or we're going to figure out the number of ways that can happen. Now we're going to figure out the number of ways that we can get 2 bad. And we have 5 in our sample, so that means 3 are going to be good. And what if we have 3 bad? Therefore, 2 are good. So we want to determine how many ways each of these can happen. How many ways are there to get 1 bad radio? Well, we only have 3 bad ones, so there's 3 ways to choose 1. How many ways can we choose 4 good radios? Combination 97, 4, because we have 97 good radios to choose from. Now let's look at how we can choose 2 bad. Combination 3, 2. We have 3 bad radios to choose from. We're choosing 2. How many ways are there to choose 3 good ones? Combination 97, 3. How many ways are there to choose 3 bad radios? Well, the only way that can happen is to choose the entire group. There's only one way that can be done. Now I'm going to choose 2 good radios, so combination 97, 2. All of these are equally likely, so that means we can take the number of outcomes in our event and divide by the number in the sample space. So my probability then will be we'll label this number in E. Combination 97, 4 plus combination 3, 2. Notice combination 3, 2 is going to be 3. If we're choosing 2, that means that's the same as choosing the one left over, the one that is not chosen. There are 3 ways that can happen. So you could just put 3 in place of combination 3, 2 if you want. And we're going to take the whole thing and divide by combination 105. I'm going to write down the individual numbers here so that you can check yourself, but once you get a little practice in with your calculator, you may be able to do this all in one calculation without writing the intermediate steps. Or I should say without calculating the individual combinations separately. Should end up with about 0.144. Let's do this another way, and I think you'll find this is a little bit easier, and you should be alert for this. Let's go back up. Okay. Okay, so what we're going to do here is we're going to use the complement. So if our event is that at least 1 in my sample is bad, in other words, 1, 2, or 3 are defective, then what is my complement? All the radios in my sample are good. Well, how many ways can this happen? How many ways can everything in the sample be good? Well, I have 97 good radios. We're going to choose all of them in the sample to be good, so that means we're going to do 97 combination 5. So our probability of the complement, we take the number in the complement and we divide by the number in the sample space. So we have combination 97, 5 divided by combination 100, 5. This turns out to be about 0.856. Once we know the probability of the complement, how do we get the probability of the original event? We subtract from 1. And so here we get 1 minus 0.856, which is 0.144, which is the same answer we got the other way by calculating the event directly. It's certainly more efficient to do this using the complement. So what you want to notice each time you have something like this, if it says at least or at most or more than a certain number in your group are good or bad or whatever, you want to ask yourself, will it be easier to calculate the number in the event or the number in the complement? If it's easier, use the complement and then subtract from 1 to get the probability that you want. Let's do another example. Let's suppose that we have a locker that has a combination lock with a wheel, you've seen these, that must be turned to 3 numbers in succession. The wheel contains the numbers 0 through 39, and we don't repeat the numbers. What's the probability of guessing the correct combination? So what is my sample space? All possible ways to choose 3 numbers. Now, does the order matter? Ask yourself this. If you chose the correct 3 numbers but did them in the wrong order, would the lock open? No, it wouldn't. So order definitely matters here. So our number of things in the sample space are permutation. How many are there to choose from? 0 through 39, so that's 1 through 39 along with 0, so that gives me a total of 40 numbers to choose from. How many am I choosing to be in my combination? 3, so 40, 3. How many correct answers are there? Well, what do we call a correct answer? That's if my lock opens. How many ways will that happen? There's only going to be 1 correct selection. We're going to have exactly the right 3 numbers, and we're going to have them in exactly the right order. So my probability that the lock opens will be the number in my event divided by the number of possibilities. So that'll be 1 divided by permutation 43. So this is about 1.687 times 10 to the negative 5th, which is, move your decimal for 5 slots. If you want to write it without the scientific notation. So this is usually called a combination lock, but what should we really call it? It's not really a combination lock, it's a permutation lock. So next time you hear anyone talking about their combination lock, you can correct them and tell them that no, it's a permutation because the order matters. Let's do one more example. The Lotto Texas game, which I have heard it described as a tax on people who cannot do math. Let's do this example and decide whether you agree. Players choose 6 numbers from the numbers 1 to 54. They don't repeat the numbers. If the player chooses all 6 winning numbers, regardless of order, he wins the big jackpot. And there are smaller prizes for matching 5, 4, or 3 of the 6 winning numbers. Now we note that we have 54 numbers altogether. How many are correct? Well, there are 6 that are correct. And these are the ones that the person in Austin or wherever has drawn them out and has decided these are the 6 winning numbers for this particular round of the lottery. 6 are going to be correct, which means that the other 48 are wrong. What is the probability that we win the jackpot? All 6 must be correct. How many ways can that happen? Only 1. Only one way this can win. Only one possible winning set of numbers is if you get all 6 exactly correct. So the probability of winning is equal to 1 divided by, okay, what's our sample space? Our sample space is going to be the number of ways that 6 numbers can be chosen from the group of 54. So that'll be combination 54, 6. So 1 over 2. One over 25,827,165. And so that gives me about 3.87 times 10 to the negative 8 ways. Not ways to win, but that's the probability of winning. What's the probability of winning second prize? Well, if you're going to win second prize, that means you get 5 right and you get 1 wrong. So my probability of winning second will be, when we're going to have the same sample space, combination 54, 6, there are, how many ways are there to choose 5 correct numbers? Well, we have 6 numbers that are correct, so if we're going to take out of the 6, we're going to choose 5. So we get combination 6, 5, which would really be 6, because choosing 5 is the same as choosing the 1 left over, and there's 6 ways that can occur. How many ways are there to choose 1 wrong number? 48, because we have 48 wrong numbers that we could choose from. So here we end up with 1.12 times 10 to the negative 5. That's for second prize. Third prize, we're going to end up with 4 right and 2 wrong. So the probability of getting third prize then, well, we're going to have the same sample space. Now we're going to choose 4 to be correct. Out of those 6 numbers, out of the 6 correct numbers, we're going to choose 4. So that'll be combination 6, 4. How many ways are there to choose 2 wrong numbers? Well, there are 48 wrong numbers to choose from. I'm going to choose 2. So we get combination 48, 2. So we end up with about 6.55 times 10 to the negative 4. Notice our probability is increasing each time. You can tell by looking at the scientific notation. Fourth prize. So that means now we're going to have 3 right, which means 3 are going to be wrong. Okay, so the probability of having this happen, same sample space. Now, how many ways are there to choose 3 right? Well, we've got 6 to choose from, choosing 3. Combination 6, 3. Now we're going to choose 3 from the 48 wrong numbers. So we get combination 48, 3. And so this turns out to be about 0.0134 for our probability. So once again, more likely than the ones before, which you would expect, and it's going to therefore have a smaller payout. I hope this helped you to understand probability involving combinations and permutations. Good luck. I'll see you next time.